we first started looking at motion diagrams, I made reference to a theorem that's beyond the scope of this treatment that said that for rigid objects, you can completely describe their motion as a combination of the translation of their center of mass and their rotation about their center of mass. So we're going to go and take a look right now at how to start describing rotations. And to do that, we'll want to define some angular variables. So we can imagine, just say, a mass on the end of a string, something like this. There we go. There's my mass on the end of the string. And let's say that it rotates through some angle theta, like so. We can use this to actually describe how this mass on the string is rotating in our 2D plane. And so we can start to define angular position. So if you recall from trig, the official definition of an angle is the arc length that gets traversed over the radius. So this angle subtends an arc length s. That's just the length along a circle that connects my object here and here. And this is the radius of my string, or just the radius of the circle we're moving in. So this is defined to be the arc length over the radius. And we usually say that the units, quote unquote, for this are radians. Now, the reason I say quote unquote about the units is they're technically a symbol. Because if you think about it, arc length has units of meters, radius has units of meters. So meters over meters, that just cancels. So really, a radian is just a fancy way of writing the number 1. So this is really just a symbol that tells us we're dealing with angles. And importantly, it has no physical dimension. So basically, you can just treat it like it's number 1. Treat like the number 1. There we go. I mentioned this because, as we'll see going along, when you're checking units, you may find that powers of radians don't match on one side of the equal sign versus the other. In fact, we can just, to show this clearly, we can just multiply both sides through by r and get that the arc length is equal to the radius times the angle. Well, the arc length has units of meters. The radius has units of meters. And then we have this symbol radian. And at first you'd look and say, oh, it looks like I screwed up or something because I got meters here, meters times radians here. But it's all okay because we just treat the radian like it's the number 1. It's just a symbol to let us know that this is an angular quantity, but we actually don't stress about it when we're checking units because it's not really a unit. So a couple of other things that we need to keep track of. By convention, if we go counterclockwise off of our reference line, so this is my reference line. So if we go counterclockwise off of that, then that is a positive angle. If we go clockwise off of that, that is a negative angle. And that may seem a little counterintuitive. The reasons are more historic than anything. Basically, this choice comes from the fact that if you look at the Earth's rotation from above its north pole, the Earth rotates counterclockwise. So to give the Earth an angular positive velocity, we say that counterclockwise rotation is positive. The other thing we're going to need to do with angular position on the way to talking about how fast things rotate is that we are also going to need our angular position to keep a turn counter. What do I mean by that? So angular position keeps a turn counter. So what I mean by that is, let's say this is my reference line here. Again, usually it's the plus x-axis, but it could be anything. This angle right here would be pi radians. And this angle here is 3 pi radians. Now, they look the same, and if you were to take the sine or cosine or the tangent or whatever of it, your calculator will give you the same answer each time. And a lot of times in trig classes, you just go ahead and treat them like they're the same. But it's important for us to keep the difference distinct. And this is because if we're thinking about rotations and trying to characterize how fast something is rotating, it makes a difference whether you're rotating through pi radians in 1 second or 3 pi radians in 1 second. So we have to keep track of the history of the object's rotation, and every time we complete a full rotation, we're going to say that we added another 2 pi radians to the angular position. So I've alluded to angular velocity, so now let's go ahead and define that officially. So angular velocity is the rate at which something is rotating. So we define it in analogy to how we did it for just regular velocity, where we can imagine taking the limit over smaller and smaller time intervals of the change in the angle over the change in time. And since this is what we mean by a derivative, we could also write this as d theta dt. So the units for this are radians per second. And again, when you're balancing these things out, we just treat the radian like it's the number 1. However, don't write an angular velocity in units of seconds to the -1. There was a push to do that a while back, so you could find some older books that do that, and everyone gave up on it for a really good reason. If you're characterizing how something is oscillating, you talk about how many oscillations per second something undergoes. And so again, it's the same deal. The units would be seconds to the -1. If you're characterizing how something's rotating, that would be radians per second. And this sort of thing turns out to lead to more, if you lazily just write this, although it's quote unquote technically legal, it tends to lead to a lot of dropped or added factors of 2 pi. So for oscillations, which we'll get into later, we always write hertz, which that is 1 over seconds. And for angular velocity, we always write radians per second, and we never write seconds to the -1 for either situation. And that's just in order to keep them straight. Alrighty. So in the original example that I was doing, and again, following through with our definition from angle, if something is rotating counterclockwise, that will give us a positive angular velocity. And if it's rotating clockwise, it will give us a negative angular velocity. I mean, you're free to choose otherwise, but if you don't say, that will be what's assumed. So looping back, no pun intended, to the example I was thinking of initially where I had a mass on the end of a string of radius r, and it was going around, well, let's make this our circle a little smaller this time. There we go. So I was going around in a circle like so. You might want to know how fast is it going translationally. Well, we can go ahead and draw a vector for that. And I can get the magnitude of the velocity, which annoyingly we call the tangential velocity, even though it's really a speed. Tangential velocity. So I'll put speed in parentheses here. We call it a velocity, but it's not a velocity because the direction's constantly changing. We're just concerned with how fast we're going. Well, what we can do is we can say that if I want to know just plain how fast I'm going, well, I'm covering some distance here along an arc. That's an arc length. And the rate at which that arc length is changing would be the speed I'm going at. Now the velocity will be, even if I'm going at a constant speed, the velocity will be constantly changing because the direction will keep changing. And velocity is a vector quantity. That's why this is really a speed, but for historic reasons, everybody says tangential velocity, even though deep in their heart of hearts they know it's a speed. So we can follow that through and say that that's ds dt. So that's the rate at which the arc length is changing. So that's the length at which the product of the radius and the angle is changing. Going back to our definition of angle, remember we found that the arc length is equal to the radius times the angle. But since the radius isn't changing, the rate of change of the product of the radius and the angle will be the same difference as the radius times the rate of change of the angle. So we can write that as radius times rate of change of the angle, like that. And we look at that and go, hey, that is our angular velocity. Now just a quick side thing here. When I'm writing my angular velocity here, this is not a W. This is actually a Greek letter omega. And the way you would draw a Greek letter omega, if we go back to that special paper that we were all using in second grade, like so. It looks something like that. It's got loopies, so a W is going to be more pointy. So if your W's are naturally loopy the way you write them, you're going to have to do something to make it clear that W and omega are different letters, because in the future they will show up in the same problems. Okay, so let's just do an example of how this can help us. And an example I can think of is, let's imagine that we've got a couple of pulleys like so. I'll make them, there we go. Yeah, that's pretty good. All right, so let's say I got a couple pulleys like so, and they are connected with fan belts, but let me go ahead and dimension in their radii. So let's say this is pulley A, this is pulley B, so radius A, radius B. We'll say that radius A, let's make it 10 centimeters. And radius B, let's say, is 5 centimeters. Now, we'll have this attached to a fan belt. Let's go ahead and draw the fan belt in purple, I guess. So, yeah, something like that. Something like that. Okay, there's my fan belt. So, if pulley A is turning at 10 radians per second, what is the angular velocity of pulley B? Well, we can tie this together via the tangential velocity. And the idea here is if we look at any point on our fan belt, and I should probably continue my fan belt along like that and along like that. So if I look at this point on the fan belt right here, it'll have to be going at whatever the tangential velocity is for a point on the end of the pulley here. And similarly, the fan belt has to be going at that same tangential velocity here. Otherwise, the fan belt would slip. So this means that at the edge of the pulley A and the edge of pulley B, the tangential velocities would have to be the same. So we can go ahead and demand that. So we can demand that the tangential velocity for pulley B be equal to the tangential velocity for pulley A. So this will be the radius of pulley A times the angular velocity of pulley A, sorry, B. Oops. And that would be equal to the radius of pulley A times the angular velocity of pulley A. All right, so then we can get that pulley B is going at RA over RB times the angular velocity of pulley A. So plugging everything in, 10 centimeters over 5 centimeters times 10 radians per second. Now, you may be asking yourself, is it okay that I didn't convert these to meters? And the answer is yeah, it's totally fine as long as the units are the same. Here they're both centimeters, so I can still cancel my centimeters and I'm totally good. And I end up with 20 radians per second. Now, if I had put in one in meters and one in centimeters, I'd either have to turn the meters to centimeters or the centimeters to meters, because when I divide, I need compatible units in order to cancel units. But here I had them both in centimeters, so there was no real need to convert to meters. Alrighty, so in the next video, we will go ahead and start to take a look at accelerations for things going around in circles. Catch you there.